This talk is about extension-based proofs in synchronous message passing models. I'm Yilun Sheng, a senior undergraduate student from Yale class, IIIS, Tsinghua University. It is joint work with Professor Faith Allen, who was my advisor when I was remotely visiting University of Toronto. In the asynchronous shared memory model, it is known that there is no weight-free algorithm to solve consensus among two or more processes using only registers. The proof of this impossibility result uses a valency argument. It is also known that there is no weight-free algorithm to solve k-set agreement problem for k+1 or more processes using only registers. K-set agreement is a generalization of consensus, in which processes need to decide on at most k different values. However, for k at least 2, the proof of this impossibility result involves sophisticated combinatorial topology. Similar results has been established in the synchronous message passing model. It is known that there is no algorithm to solve consensus for t+2 or more processes in at most t round, when at most one process crashes each round. The proof of this impossibility result also uses a valency argument. It is also known that there is no algorithm to solve k-set agreement problem for kt plus k plus 1 or more processes in at most t rounds, when at most k processes crash each round. However, for k at least 2, the proof of this impossibility result also involves sophisticated combinatorial topology. Many researchers wondered whether combinatorial topology was necessary for this impossibility result about k-set agreement. In the paper Why Extension-Based Proof Fail, the authors attempt to answer this question for the asynchronous shared memory model by defining the class of extension-based proofs, which is a generalization of the valency arguments. They showed that there is an extension-based proof of the impossibility of solving consensus, while there is no extension-based proof of the impossibility of solving k-set agreement for k at least 2. So valency arguments cannot be used to prove this impossibility result. Subsequently, another group of authors defined a simpler class of proofs for the iterated immediate snapshot model, when all processes output values in the same round. They also show that there is no proof of the impossibility of solving k-set agreement in their class. Our first contribution is a definition of extension-based proofs for the synchronous message passing model. Then we show how to express the valency argument for the lower bound for consensus as an extension-based proof. Our main result is that we show that there is no extension-based proof of the impossibility of solving k-set agreement in synchronous message passing model in t rounds for kt plus k plus 1 processes, when at most k processes crash each round, where both t and k are integers greater than 1. Before presenting our class of proofs, I want to quickly review the definition of extension-based proofs from the paper Why Extension-Based Proofs Fail. An extension-based proof is a sequence of interaction between a prover and an algorithm that proceeds in phases. The algorithm claims to solve a task in a weight-free manner, while the prover tries to show the algorithm is incorrect. In the first phase, the prover can ask queries from any configurations reachable from initial configurations. The prover may ask queries about what happened when a process takes one step from a configuration C it has reached. The prover may also ask whether there is a sequence of steps by process in Q from a configuration C it has reached, such that some process in Q outputs the value M in the resulting configuration. The algorithms either respond with such a process and a sequence, or since they do not exist. After making finitely many queries in phase R, the prover must choose a configuration CR it has just reached in this phase, and start phase R plus 1. Phase R plus 1 is the same as the phase R, except that the prover can only ask queries for configurations reachable from CR, the configuration it has just chosen. During the interaction, the prover wins when it can show the algorithm is incorrect. Specifically, the prover wins if the algorithm responds with a configuration in which the outputs of processes violate the task specifications, as it has demonstrated that the algorithm does not solve the task. The prover wins if there is an infinite number of phases, as it has demonstrated that the algorithm is not weight-free. The prover also wins if the algorithm provides contradictory information. Otherwise, the algorithm wins. Now we present the definition of our class of extension-based proofs for synchronous message passing. Similarly, an extension-based proof is a sequence of interaction between a prover and an algorithm that proceeds in t+1 phases. The algorithm claims to solve a task in t rounds, while the prover tries to prove the algorithm is incorrect. During phase 0, the prover asks whether there is a sequence of t round sigma from an initial configuration C prime, in which only process in queue takes steps. At most, U process crash each round, and some process outputs M in the resulting configuration C prime sigma. The algorithm either responds with such a process and a sequence of rounds, or says they do not exist. At the end of phase 0, the prover chooses an initial configuration C0 and proceeds to phase 1. During phase R, where R is between 1 and t-1, the prover considers configurations C prime that can be reached from CR-1 by a one-round schedule sigma prime R, in which at most K processes crash. Recall that CR-1 is the configuration chosen by the prover at the end of phase R-1, the previous phase. The prover asks whether there is a sequence of t-R rounds sigma from C prime, in which at most U process crash each round, and some process outputs M in the resulting configuration C prime sigma. The algorithm either responds with such a process and a sequence of rounds, or says they do not exist. At the end of phase R, the prover chooses one round schedule sigma R, in which at most K process crash, and proceeds to the next phase, with CR equals to CR-1 sigma R be the resulting configuration. In phase T, the prover considers configurations that can be reached from CT-1 by a one-round schedule in which at most K process crash, and asks what each active process outputs in those configurations. At the end of phase T, the prover chooses a one-round schedule sigma T from CT-1, in which at most K processes crash, and sets CT be the resulting configuration. Similarly, during the interaction, the prover wins when it can show the algorithm is incorrect. Specifically, the prover wins if the output in the resulting configuration CT violates the task specifications, as it has demonstrated that the algorithm does not solve the task. The prover wins if some process has not terminated in the resulting configuration CT, as it has demonstrated that the algorithm does not solve the task in T rounds. The prover also wins if the algorithm provides contradictory information. Otherwise, the algorithm wins. To prove that there is no extension-based proof for the impossibility of k-set agreement in asynchronous shared memory model, the authors of the paper Why Extension-Based Proof Fail adaptively constructed an adversarial k-set agreement algorithm that wins against each prover. Since no correct algorithm exists, the adversarial algorithm will be different against different provers. In other words, the adversarial adapts its responses based on what queries the prover asks and what configurations it chooses. In our paper, we do the same thing. We first introduced the flood-mean algorithm, which motivates parts of the construction of our adversarial algorithm. In the flood-mean algorithm, every process maintains an adopted value, which is initially its input. Each round, every process first sends its adopted value to all other processes, and then updates its adopted value to be the minimum of its adopted value and the value it received this round. Eventually, at the end of round T, every process outputs its adopted value at that moment. There are two important facts about the flood-mean algorithm. First, the set of adopted values in one round is a subset of adopted values in the previous round. This ensures validity. Secondly, the number of distinct adopted values after one round is at most the number of processes crashed in this round, plus 1. Consequently, flood-mean solves k-set agreement when less than k processes crash in some round. Also, if k processes crash in each of the T rounds, then it still solves k-set agreement in T rounds, provided the number of processes was at most kt plus k, since at most k processes output values after T rounds. However, it does not solve k-set agreement in T rounds for kt plus k plus 1 processes. Next, we define a family of algorithms Bm star, parameterized by the value m star. In the first T-1 rounds, Bm star behaves like the flood-mean algorithm. In round T, however, Bm star does something more complicated. The important thing is that every process outputs a value that was adopted by some process that has not crashed at the end of round T-1. In other words, the set of output values is a subset of adopted values at the end of round T-1. There are also three important facts about the Bm star algorithm. First, if at most k-1 process crash in one of the first T-1 rounds, then, as in flood-mean, there are at most k distinct adopted values at the end of round T-1. Hence, there are at most k distinct output values. So Bm star solves k-set agreement in this scenario. Second, if at most one process has adopted value m star at the end of round T-1, then Bm star also solves k-set agreement. Third, no algorithm, including this Bm star, always solves k-set agreement for kt plus k plus 1 process in T round. We now present our adaptive adversarial algorithm A. In the first T-1 rounds, the adversarial algorithm behaves like flood-mean. In the last round T, the adversarial algorithm behaves like Bm star, where m star is the smallest adopted value held by at most one active process in Ct-1, the configuration chosen by the prover at the end of phase T-1. In the paper, we explain why A wins against every prover. Thus, we have shown that in the synchronous message passing model, there is no extension-based proof that more than T rounds are necessary to solve k-set agreement among kt plus k plus 1 processes, when at most k processes crash each round. There are a number of problems that remain open concerning extension-based proofs in synchronous message passing model. Can our lower bound proof be extended to more processes? Can it be extended to allow any number of processes to crash each round? It would be also interesting to show that there are other tasks that do not have extension-based lower bound proofs. Finally, other definitions of extension-based proofs for synchronous message passing can be investigated.